Hi, the rest of chapter 4 is over oxidation numbers, balancing redox equations, molar concentrations, and titrations. First, let's start with oxidation numbers. What is an oxidation number? Oxidation number is nothing but what we used to call it charge. So for monoatomic ions especially, we call it a charge on the monoatomic ion. Like for sodium ion, it's +1, so oxidation number is +1. For magnesium ion, the charge is +2, so its oxidation number is +2. But there are some rules to determine each category of atoms or elements oxidation number. Let's go over them real quick. You have them in your PowerPoint slides, in your book, and these are essential to understand how to determine the oxidation number. So don't forget to review them first. For the elements, for each atom in elemental form, the oxidation number is 0, because what you see here, you just see the neutral atoms without any charge, so the charge or oxidation number is 0. For a monoatomic ion, we just said that the charge is the same as oxidation number, so it's equal to the charge on the ion. Like for example, for sodium ion is +1, for calcium ion is +2, and so on. For oxygen, most of the time the oxidation number is -2. That's what you refer as charge again. The exception is in hydrogen peroxide, where oxidation number of oxygen is -1. As we said, this is an exception. For hydrogen, its oxidation number is +1 most of the times. The exception is that when hydrogen is in combination with a metal. In that case, exceptionally, the oxidation number of hydrogen instead of +1 will be -1. Next rule, for halogens, group 17 elements. For fluorine, oxidation number is always -1. For chlorine, bromine, and iodine, in binary compounds like in NaCl and in magnesium bromide, MgBr2, their oxidation numbers is -1. For the compounds, the sum of oxidation numbers of atoms must be equal to 0. And for polyatomic ions, sum of oxidation numbers of atoms must be equal to the charge on the ion. I have 2 examples for you that you can apply all of these oxidation numbers and finish it with rule number 6. Ready? For KMNO4, for potassium permanganate, we are supposed to determine all the oxidation numbers. For group 1 elements, if it forms a monoatomic ion, what would be the oxidation number on it? +1, right? For oxygen, what did we say oxidation number would be? Most of the times would be -2. And according to rule number 6, the sum of oxidation numbers of the atoms must be equal to 0 for a compound. You might say, how about manganese? You are solving for manganese because there is no rule for transition elements. So you know that for monoatomic cations, for group 1, the charge or the oxidation number is +1. For oxygen is -2. So let's apply all of these rules. You have 1 potassium with a +1 charge plus 1 manganese with an unknown oxidation number. I normally use the same symbol for the element. You can use X, Y, Z, whatever you want. Plus 4 oxygens. -2 is the oxidation number on each one. Rule number 6, oxidation number, the sum of oxidation numbers of all the atoms in a compound must be equal to 0 because there is no charge anywhere. When you solve for manganese, this simple quadratic equation, what would be the oxidation number for manganese? Isn't it +7? Right? So the same thing let's find the oxidation number for chromium here. What is the oxidation number on oxygen? It's not hydrogen peroxide, so it's -2. So let's do it. 1 chromium, we are solving for its oxidation number, plus 7 oxygens, -2 oxidation number on each one. Rule number 6, sum of oxidation number of atoms in a polyatomic ion will be equal to that charge. Okay? So if you solve this equation, what would be the oxidation number for chromium? It would be -14, then -12, +12, and, oh, I'm sorry, there is a mistake here, 2 chromium. So oxidation number of chromium is going to be +6. If you add them up, the sum must be -2. Make sure you work on enough examples, and you can ask if you have any questions later. The next concept is about oxidation and reduction reactions. In general chemistry, the description for oxidation is electron loss when an element loses electrons, and reduction means electron gain when an element gains electrons. And so the oxidation reduction reactions that we shorten it in redox reactions is called electron transfer reaction. Electron transfer from an element which is oxidized and loses electrons to the element which is reduced and gains electrons. So let's look at this equation. Let's determine which element is oxidized, which one is reduced. What is the oxidation number of Fe here? For a monoatomic ion, it's +3. For a monatomic ion, it's the same as the charge. What is it for iron? Iron is in its elemental position, so it's 0. Rule number 1. So the oxidation number reduced from 3 to 0. So this is reduction. The oxidation number reduces, means Fe ion gained 3 electrons to change to elemental iron. So the same thing for magnesium. What is the oxidation number on a magnesium atom, the element? Rule number 1, 0. What is the oxidation number on a monoatomic ion? The same as its charge, right? So oxidation number increased means magnesium has lost 2 electrons to change to magnesium ion. So this is our oxidation part. So which one was oxidized? Tell me. Iron, right? Iron 3 reduced, right? So I call it oxidizing agent. Why? Because by reduction, when it gains electrons, it induces oxidation in magnesium. So what is an oxidizing agent? Is the substance which is reduced itself and induces oxidation in the other atom. For magnesium we said it's oxidized, right? Means it loses electrons. So is it okay if I say it's reducing agent? Because by losing electron, it induces the reduction to iron ion. So it's the reducing agent. So knowing these terms is also important. The element which is oxidized is reducing agent. The element that is reduced is oxidizing agent. We play with these two words, with the terms. All right. So let's balance oxidation reduction reactions using half reaction method. We are using the same exact equation. I'm going to cut it to two half reactions. Didn't we just say that iron was reduced and magnesium was oxidized? So after you determine which element is oxidized, which element is reduced, let's write them in front of oxidation half reactions and reduction half reactions. So oxidation number of iron changed from +3 to 0. It was reduced, so I have to use the reduction half reaction. Fe changed, Fe3 changed to Fe, right? Let me just write it a little bit towards the right side. And which one is the oxidation half reaction? Magnesium that changed to magnesium ion. In balancing the equations using half reaction method, you must have both the mass or the atoms balance and also the charges balance. So far, in balancing your equations, you just took care of the atoms. Here, because it's about electron transfer, you're supposed to cut it into two half reactions and take care of both mass and charge balancing. So let's take care of the atoms first. And we start with the oxidation half reaction. Going from magnesium to magnesium ion. How many magnesium atoms do we have on the left? We all see one. And we see one on the right. So 1 and 1, there is no change in the number of atoms. But how about the charges? The charge here is 0 and here is +2. How can I balance it out? By using electrons. Don't forget, you always add electrons to more positive side. So how many electrons do you need to add to more positive? Which is my more positive side? This side, right? Because the charge is 0 here, here is +2. So I should add how many electrons? You would say 2, I'm sure. So we are done with oxidation half reaction. Let's take care of the reduction half reaction. Fe3 changed to Fe, 1 atom of iron, 1 atom of iron. Again, there is no change in the number of atoms, but the charge here is +3, the charge here is 0. I should add enough electrons to more positive side to balance it. How many electrons? 3 electrons. Because it's electron transfer reaction, I should be able to cancel the two electron amounts from each other and add these two half reactions to go back to the original reaction. But can I do this? Can I cancel them out? No. You need to multiply both of them by a number that makes them the same. Because we have an even and an odd number, let's cross multiply them. The first reaction by 3, the second reaction by 2. So we change it to, it's too early to add them to each other. So we will continue here. 3 magnesium, change to 3 magnesium ion plus 6 electrons. And for the second one, what was it? 2 Fe plus 6 electrons gives 2 Fe, right? You are multiplying these by all of the, by two sides, by both sides, and the same. Okay? So let's go back. Now we are able to cancel the electrons from each other. You are ready to add them and have the final equation. 2 Fe plus 3 Mg on the left side, and let's stick with Fe. 2Fe. The order doesn't matter. You can write it anywhere. Okay? So, even at the end, the number of atoms and the charges must be balanced. 2Fe, 2Fe, 3 magnesium, 3 magnesium, 2 times 3, positive 6, 3 times 2, positive 6. Now, before we finish this part of the video, I would like you to work on this equation on your own based on half reaction method, and if you have any question, ask me. In the next video, I will finish this chapter by explaining titration, dilution, and molar concentration.